Welcome, my name is Dr. DrWedding, and this is DrWedding DC19. Solving series parallel circuits. In this video, you will learn how to solve a series parallel circuit, like the one shown below. This method works with circuits with one power supply. A series parallel circuit is not a series circuit, so the rules you learned about a series circuit do not apply. The current is not the same throughout the circuit. The resistors do not add up to the total resistance, and the voltage divider rule does not apply to this type of circuit. A series parallel circuit is also not a parallel circuit, so the rules you learned about a parallel circuit do not apply. The sum of the currents is not the total current. The voltage is not the same across all the resistors, and the current divider rule does not apply to this type of circuit. Even if these rules do not apply to the entire circuit, they do apply to smaller areas of the circuit. So, you will use the rules you already know, but you will need to switch back and forth between the series rules and parallel rules to solve the circuit. The terms zip and unzip are terms I use when I teach this procedure. I use the term zipping when multiple resistors are compressed into a single resistor, and I use the term unzipping when one resistor is expanded into multiple resistors. Using these terms, I can break the solution into three easily understood steps. The three steps to solve a series parallel circuit are: Step 1. Zip the circuit until there is only one resistor. Step 2. Calculate the total values for the circuit. Step 3. Unzip the circuit to get the remaining values. Step 1 is zipping the circuit. To zip the circuit, cover up the circuit and slowly uncover the resistors starting from the resistor that is the farthest from the power supply. When you see two resistors, combine them. The rules for combining resistors are the rules you already know. If the resistors are in series, add them together. If the resistors are in parallel, use the parallel resistor equation. Next, redraw the circuit with the newly combined resistor. You will need to repeat this process until there is only one resistor in the circuit. This one resistor is the total resistance for the circuit. Here is a demonstration of how to zip this small circuit. We will call this circuit A, and it is the original circuit. First, cover up the circuit with a piece of paper. Some students find it helpful to draw a power supply on the sheet of paper they are using to cover the circuit. This may help you recognize if the resistors are in parallel or in series. Slowly uncover the resistors starting from the resistor that is the farthest from the power supply. Continue until you can see two resistors. In this circuit, you will expose R2 and R3, and you will see they are in parallel. They will be combined into a new resistor called R23. Using the parallel resistor equation, the resistance of R23 is 1.54 kilo ohms. When R2 and R3 are combined, one of the resistors will be removed from the circuit and the other resistor will be replaced with R23. It does not matter which resistor is removed and which is replaced. Removing R3 from the circuit and replacing R2 with the new R23 value, a new circuit is generated. This new circuit is renamed Circuit B. Circuit B is a series circuit. R1 and R23 will be combined into a new resistor called R123. Because resistors in series can be added together, resistor R123 is equal to 2.54 kilo ohms. Just like before, one of the resistors will be removed and the other will be replaced with R123. R1 was removed from the previous circuit and R23 was replaced with R123. This new circuit was renamed Circuit C. Because this circuit only has one resistor, it is the end of Step 1. Step 2 is finding the total values for the circuit. The single resistor generated by the zipping process is the total resistance for the circuit. Using Ohm's law, you can calculate the total current for the circuit. This information is used to fill in the bottom row of the table. Step 2 is demonstrated here. The total resistance is filled in the bottom row of the table. And using Ohm's law, you can find the total current. In this example, the total current is 3.94 milliamps. Step 3 is unzipping the circuit. The circuit is unzipped in the opposite order that it was zipped. Each time the circuit is expanded, a resistor will break apart. If the resistor breaks into series resistors, copy the current from the previous circuit. If the resistor breaks into parallel resistors, copy the voltage from the previous circuit. Find the unknown values with Ohm's law. And repeat this process until the circuit is solved. The unzipping process is demonstrated here. Because circuit C is solved, we need to move back to circuit B. Resistor R123 in circuit C becomes the series resistors R1 and R23 in circuit B. And when a resistor breaks into series resistors, you copy the current. So, the 3.94 milliamps flowing through R123 in circuit C is copied into resistor R1 and resistor R23 in circuit B. We don't have a spot on the table for R23, so we will create a temporary row. This row will be discarded later. You can see that the total current has been copied into R1 and R23 on the table. Using Ohm's law, the voltages across R1 and R23 can be calculated. This information is filled in on the chart. It should be noted, when you copy the current from one circuit to another, you split the voltage. This is helpful to double-check your work. When the total current was copied into R1 and R23, the total voltage was divided between R1 and R23. Because circuit B is solved, we need to move back to circuit A. Resistor R23 in circuit B becomes the parallel resistors R2 and R3 in circuit A. And when a resistor breaks into a group of parallel resistors, you copy the voltage to the new circuit. So, the 6.06 volts across R23 in circuit B is copied across R2 and R3 in circuit A. These two voltages are added to the table. Using Ohm's law, we can find the last two currents that are needed to fill in the table. It should be noted, when you copy the voltage from one circuit to another, you divide the current. This is helpful to double-check your work. When voltage across R23 was copied to the new circuit, the current through R23 was divided between R2 and R3. So, the solution to this circuit is shown in the table on the right. When you are done, you may want to check to see if your answers make sense. You can do this with Kirchhoff's voltage law and Kirchhoff's current law. If you use Kirchhoff's voltage law, you can see that no matter what path you take, the voltage will sum to zero. If you use Kirchhoff's current law, you can see that the sum of the currents at the upper node is equal to zero, and the sum of the currents at the lower node is also equal to zero. Here is example 1. If you want, you can pause the video and try to solve this problem on your own. When you restart the video, the solution will be given. Start by creating a table and filling in the known values. This original circuit is named Circuit A. Draw a power supply on the edge of a piece of paper and use it to cover up the circuit. Slowly drag the paper towards the power supply, exposing the resistors one at a time. When you see two resistors, determine if they are in series or in parallel. In this example, R4 and R5 are in series. They can be combined into a new resistor named R45. Update the circuit by removing one of the resistors and replacing the second resistor with the new resistor. In this example, R4 was removed, and R5 was replaced with R45. This new circuit is now called Circuit B. The process is repeated. The circuit is covered by a piece of paper. The paper is slowly dragged across the circuit to expose the resistors. When two resistors are exposed, determine if they are in series or in parallel. In this example, R2 and R45 are in parallel. They are combined using one of the parallel resistor equations. The new resistor is named R245. R45 was removed, and R2 was replaced with R245. This updated circuit was renamed to Circuit C. At this point, the circuit is obviously a series circuit, so we do not need to cover it with a piece of paper. The three series resistors are combined. This resistor is our 1, 2, 3, 4, 5, and it is the same as our total. The circuit is updated and renamed to Circuit D. Because there is one resistor, we are done zipping the circuit. Using this circuit, we can start to fill in the total row at the bottom of the table. Using Ohm's law, you can get the total current. With the bottom row filled in, you are done with step 2 and you can start unzipping the circuit. To unzip the circuit, you need to go through the zipping process backwards. So, copy Circuit C under Circuit D. You can see that resistor R1, 2, 3, 4, 5 broke into 3 resistors, R1, R2, 4, 5, and R3, and these resistors are in series. Because current is the same in a series circuit, you can copy the current from R1, 2, 3, 4, 5 into R1, R2, 4, 5, and R3. You can copy the currents onto the chart, but this chart does not have a row for R2, 4, 5. So, we will have a temporary row that will be deleted when we are finished with the circuit. Using Ohm's law, you can find the voltages across each of the 3 resistors. When you copy the current from one circuit to another, you will break the voltage. In this example, the 50 milliamps was copied to 3 resistors. So, the 10 volts that was across the resistor was broken up into 3 pieces. Once you know V, I, and R for all of the resistors in Circuit C, you go back to Circuit B. Resistor R245 breaks apart into resistors R2 and R45. When a resistor breaks into parallel resistors, you copy the voltage. Because in a parallel circuit, the voltage is the same across all of the resistors. So the voltage across R245 is copied across R2 and R45. A temporary row is added to hold the information about resistor R45, and the voltages are added to the table. Using Ohm's law, you can find the 2 missing currents. When you copy the voltage from one circuit to another, you will break the current. In this example, the 2.5 volts was copied to 2 resistors. So, the 50 milliamps that was through the resistor was broken up into 2 smaller pieces. When all of the values in Circuit B are known, you need to move back to Circuit A. Resistor R45 breaks apart into 2 series resistors R4 and R5. Because R45 became R4 and R5 in series, the current through R45 is copied to these 2 resistors. These currents are added to the table. Using Ohm's law, you can find the voltage drops across both of these resistors. When you copy the current from one circuit to another, you will break the voltage. In this example, the 25 milliamps was copied to 2 resistors. So, the 2.5 volts that was across the resistor was broken up into 2 smaller voltages. You can now erase the temporary rows, and you will have the final answer. You can double-check your work by using your values to verify Kirchhoff's current law and Kirchhoff's voltage law. If either of these laws fail, you have made a mistake. Here is example 2. If you want, you can pause the video and try to solve this problem on your own. When you restart the video, the solution will be given. Start by creating a table and filling in the known values. This original circuit is named Circuit A. Resistor 5 and resistor 6 are the first two resistors to be combined. Resistor 5 and resistor 6 were replaced with R5-6. The new circuit is named Circuit B. Resistor 4 and resistor 5-6 are in parallel, and they are the next two resistors to be combined. Resistor 4 and resistor 5-6 are removed, and resistor 4-5-6 replaces them. The new circuit is named Circuit C. When exposing the resistors, sometimes you get a circuit that can't be combined, such as this one. To fix this problem, you can combine R2 and R3 that are between the nodes. R2 and R3 are in series, and R2-3 will take their place. The new circuit is named Circuit D. R2-3 and R4-5-6 are now in parallel, and they can be combined. When R2-3-4-5-6 replaces the two parallel resistors, Circuit E is created. Circuit E is a series circuit, and the last two resistors can be combined. Circuit F is the end of the first step. The resulting 5K ohm resistor is the total resistance. The total resistance is added to the table. Using Ohm's law, you can find the total current. This value is then added to the table. Now that the totals are known, you can start step 3, the unzipping process. Because the total circuit F is solved, you need to step back to circuit E. The resistor was broken into two resistors in series, so the current is copied to R1 and R2-3-4-5-6. Using Ohm's law, you can get the two missing voltages. With circuit E solved, you need to move to circuit D. The resistor broke into two parallel resistors, so the voltage across R2-3-4-5-6 is copied to R2-3 and R4-5-6. You can now find the two missing currents using Ohm's law. With circuit D solved, you need to move to circuit C. R2-3 broke into R2 and R3, and these are in series. So, the R2-3 current is copied to circuit C. And just like before, you can find the missing voltages using Ohm's law. With circuit C solved, you need to move to circuit B. R4-5-6 broke into R4 and R5-6, and these are in parallel. So, the R4-5-6 voltage is copied to circuit B. Now you can find the missing currents using Ohm's law. Finally, you are back to the original circuit. R5-6 broke into R5 and R6, and these are in series. So, the R5-6 current is the current through R5 and R6. And you guessed it, the missing voltages can be found using Ohm's law. You can remove the temporary rows on the table, and the final answer is left. You can check your work using Kirchhoff's current law and Kirchhoff's voltage law. I hope this video helped you understand how to solve series parallel circuits. This topic is very important to understand because zipping a circuit is used through the rest of the course. If you find these videos helpful, please like the video, leave a comment, and subscribe to my channel. This is the only way I can continue to make these videos.